Hello and welcome back to another episode. I am your host Kaivalya Apte, and this is the Geek Narrator podcast. On this show, we have talked about observability and SRE, right from best practices to how observability infrastructure looks like and what are the challenges in building one. And today I'm joined by Frederic, who is coming again on the show for sharing more insights, but specifically into the observability agents and specifically on eBPF and how to collect profiling data and challenges around it. So in the last episode, we talked about the entire architecture of observability and building continuous profiling, challenges around that, like right from the agent level to the storage formats and but yeah, today let's go deep into the agent. And with that, welcome Frederic. I'm really excited to have you again on the show. And for folks who haven't watched the previous episode, and there have been more people following the show now, so probably they don't know about you. So let's get started with an introduction about yourself, about what you're currently doing, and then we can go deep into the agent.
Sounds good. So yeah, first of all, thanks so much for having me again. Of course, love talking about all of these things. So kind of my background is in all things sort of in the intersection of observability and Kubernetes, maybe even more specifically everything kind of Prometheus and Kubernetes. I'm a maintainer of the Prometheus project. I actually happen to be a maintainer of the Tanos project as well. Although admittedly, I haven't been working too much on those projects very lately. Yeah, and then I'm the creator of the Prometheus operator, which is like a very popular thing to use to run Prometheus on Kubernetes. And I served as the tech lead for the special interest group for instrumentation on the Kubernetes project for 4 or 5 years. So really kind of, if anybody's using Prometheus and or Kubernetes or anything observability related to those projects, they probably used at least some of the code that I've touched. And yeah, what kind of led me to starting this company called Polar Signals and spend a lot of time with profiling and ultimately continuous profiling is that my teams, so I originally, when I started all this journey of monitoring and Kubernetes, that started at CoreOS for me. I don't know if people still remember CoreOS. And then CoreOS was acquired by Red Hat in 2018. And I was at that point kind of architect for all things observability at Red Hat. And it was kind of this this moment where I read this paper that Google had published a couple of years before that called Google-wide profiling, where they described how they're always profiling all of their infrastructure and all of their applications all the time and all the amazing benefits that they were getting out of that, whether it's simply always having the right performance profiling data available to kind of optimize specific interactions, to make sure that API calls are super fast, to kind of cost optimization, because if you can do the same thing with less CPU cycles, well, that at Google scale means you can build less data centers, which is obviously huge, right? But all sorts of other interesting things. And I felt like that was something that my teams actually needed really badly, because we were profiling all of our software all the time. And for those who aren't maybe super familiar with profiling essentially allows us to understand down to the source code line number where resources such as CPU time is being spent. That kind of concept has been around ever since software engineering has, because we always needed to understand where is my program spending time so that I can use that information to improve it. And continuous profiling is then essentially this evolution of, I'm not just looking when on demand and ad hoc, when I happen to be looking, right? I'm always doing this. And historically, this kind of came with a lot of baggage, because it was historically viewed as a process that adds a lot of overhead to my application. So people were kind of afraid of doing this in production. But Google kind of showed that they are actually doing this. So, at the very least, there was some literature that said this is definitely possible, even if Google hadn't published exactly how they're doing it. And long story short, that's kind of how it snowballed into starting this company, and ultimately how we ended up building a profiler using eBPF.
Some, yeah, I mean, as you said, there are like many challenges. It's very interesting how you keep a balance between providing enough information while keeping the overhead less. And sometimes I think we as software engineers will look at things like, for example, profile data or traces or stack traces and stuff like that. And we don't kind of understand the engineering that goes behind, connecting all those dots and, giving you a good picture of your system, specifically low level details. And we are going to get into that, like why it is so challenging, why it is such a cool thing to have. And that will probably allow us to understand the amazing engineering that goes behind it. I have worked with different systems and talked about performance, and but there are different systems that deal with different types of performance problems as well. And there's always this question, as you also said, that before let's say eBPF or any research that went behind it, it was really a high amount of overhead, and people used to ask, like, why do you need continuous profiling? Why can't you deal with on demand? So what are your thoughts on that? Like, why do you think continuous profiling is such a game changer? And even if there is like overhead, there's cost attached to it, even if like you're using a third party tool like Datadog or something, like there's always cost. So how do you prove the business value in terms of what do you get out of profiling?
Yeah, absolutely. So, but before we kind of dive into that, I just want to say, with this modern tooling, you also get it at less than 1% in overhead, right? So it's essentially not noticeable. But let's assume for a second that that isn't true. So the thing with continuous profiling is it's kind of the same evolution that we went through from the 2000s to the 2010s with kind of, let's just say, monitoring and metrics for a second, where before that we had stuff like Nagios checks, right? Where we were checking constantly, is my site up? Is my site up? Is my site up? Is my site up? Right? And that was more or less the extent of monitoring that was prevalent, right? And all of a sudden, that this next generation of monitoring tools with like Prometheus and Datadog were also very inspired by what Google and now Meta had been doing internally, which is essentially performing alerting on time series, right? You collect some piece of information all the time, and you don't alert immediately when your site is down. You alert based on some state or some duration of state on the time series. And that allows for much more complex and much more sophisticated and much higher quality alerting, because all of a sudden we can work with error budget and all of this stuff, right? We can measure latencies over time as the users are experiencing them, all of these types of things, right? And I kind of see continuous profiling as that same evolution where we're not, doing individual checks and doing on-demand profiling here and there. We're actually very systematic about it, right? We're not just saying, hey, in this one time when I looked at it for a 10-second period of time, everything was good, right? Everything was performing the way that we were expecting it to. And so part of continuous profiling is just, always having the right data and catching kind of intermittent issues, things that are really difficult to get the right data for. The super classic example here are like kills, right? Typically, you only realize that there's a problem once the process has already died, right? And at that point, all the interesting data is gone, right? And so the simplest possible thing that you could come up with is with continuous profiling, you don't need to kind of try to reproduce this state anymore. All you do is query the data right before the kill happened, and boom, you have immediately the right profiling data get on with your job and actually fix the problem, as opposed to kind of searching through this needle in the haystack, trying to reproduce, which maybe you'll never be able to do, and then kind of trying to find the right piece of data. So that's kind of, in my mind, this like evolution of to being very systematic about profiling, rather than, it just happens to be a thing that I can measure here and there.
I think it makes a lot of sense, and I've been there. Like some problem happened, like out of memory error or anything like that, and then we go and try to reproduce it, and it never happens, or it happens but we are not again able to collect the data and so on.
You're not looking
yeah,
in that
exactly.
Yeah.
So it's like a never ending cycle, and then probably we just end up giving up, just to wait and when it happens again we'll have a look again. But I think it's totally it's really powerful to have this continuous stream of data, so you can react quickly. So the feedback cycle is really quick, and you don't have to spend a lot of time reproducing it, because reproducing such problems can be time consuming and even impossible in certain cases, right?
100%.
So I think that makes it clear. With this, let's try to understand what kind of, like, when we say profiling data, I think you briefly mentioned that, okay, up to like the lowest level possible, at a function level, for example, how much CPU it is taking, how much network usage is, memory usage, and stuff like that. What do we mean by profile data, and what does it have exactly?
So at the most fundamental level, all that profiling data is a collection of stack traces, right? That's kind of the like most fundamental piece of information that we can think of in profiling. Some formats kind of accumulate and say, I've seen this stack trace multiple times, but there are other formats that kind of, and this happens to be what we do. We store every single individual stack collection so that we can say specifically, this happened exactly at this millisecond or nanosecond in time. And this is useful because then we can kind of not just say, over the last week, this function used so much, so and so much CPU time, but we can also go and do a very detailed analysis and say, okay, actually the code, first did this action and then ended up doing this other thing and then went back to it, stuff like that, right? So ultimately, it kind of depends on the format, but most fundamentally, it's really just about, I'm collecting stack traces and potentially attaching a number to it. How often have I seen it? How often has this stack trace allocated memory? How often has it allocated memory that hasn't been freed? Stuff like that.
Okay. So the simplest mental model is you're probably, looking at some events at CPU level, memory level, and, counting those events for a given time range. And that can be like even nanoseconds. And that gives you an understanding, so you can look at really granular level what exactly was happening at this point of time.
Exactly.
And you mentioned something about some implementations or some formats reuse some parts of the stack trace, right? Can you show, like, can you give more examples, or let's say talk a bit more about that, like what are the advantages there of reusing, or what are the disadvantages, and so on?
Yeah, so when I talk about a stack trace, let's maybe break down for a second what I mean by that, right? So a stack trace, most people have maybe seen it when there's an exception that happened or something in your application, and it crashes, and it just wants to say, hey, this is the point where I crashed, right? And so that is a stack trace, and essentially, if we store it in some structure, what that is just a list of locations, and that location may include a function name, it may include the file name, it may include the line number, right? And we have a list of those. And so typically, the top one is the function. Let's stick with the example of the exception. exactly where the exception happened, right? And then everything underneath is just the functions that ended up calling each other that led to this specific function executing with whatever variables that may have caused it to actually crash in that moment.
Mm-hmm.
And at the very bottom, we usually see our main function or whatever. If we're talking about an application that is written in C or C++, we quite literally see the libc mainframe. So that is, when I say a stack trace, that is what I mean, a list of locations that ultimately tell us which functions called which other functions.
Mm-hmm.
And then we can prescribe different meanings to this. I think the most useful one is to think about most, because it also tends to be the most widely used profiling data, is CPU time. So how much have I seen the same function be executed by the CPU, right? And essentially the way we determine this is, let's do a very simple example. We have a single CPU in our system with a single core, and I sample 100 times per second the current stack trace, right? And we figure out, what is the current function stack trace? What is the current function stack trace? Over and over and over and over. And if we grab 100 samples per second, and 90 of those samples say it was in function A, then we can statistically say, 900 milliseconds were spent in this function. And the longer we do this, the higher the statistical significance gets, basically.
Mm-hmm.
And significance actually happens very, very quickly already. So at 100 samples per second, within a few seconds, we already have very strong significance. And so in a continuous setting, typically we actually say that a lower sampling rate is already sufficient. So in our profiler, for example, we profile each CPU core at 19 hertz. And that, across a couple of minutes worth of time is already very, very, very significant. So yeah, that's ultimately how we build these statistics, so that we can say definitely this function is interesting to look at, because over the last 10 minutes, we've seen it for 50% of the time.
Okay, that's pretty cool. So you are just looking at at certain sample rate, you're looking at the current stack trace, and for each function you're looking at, if I still see the function, if not, that function is already executed, and then you can take the last sample time and calculate how much time it might have taken. And if
it's more
yeah.
Sorry, it's a little bit different. So it's more like if we sample at 100 times per second, then we can statistically say each stack trace that we've seen, 10 milliseconds were spent in this. Now, obviously, that is not necessarily true, but the longer we do this sampling, the more sure we can be that the bigger samples that we see are actually true, right? There's no accidental sampling happening anymore, because those things kind of get dwarfed away, and only the things that truly are significant remain.
Okay, that's quite interesting. And what kind of data structures are used at this level, where you're collecting, let's say, 100 samples every second, and then of course it's like a list, or let's say a stack trace. How do you make sure that operations are really performant, data structure and algorithms wise?
Yeah, great question. So the long answer is it depends, or the very short answer is it depends. The long answer is kind of the medium answer is we try to store as little as possible, because even though obviously we care a great deal and we have engineered from the very ground up that this profiler is super low overhead, we still need to be careful about that. And so one of the things that are actually really expensive in software are memory allocations. Now, we actually have a great trick in eBPF, which is no memory allocations are allowed, basically, or all memory has to be statically allocated, and the stack itself has very limited amounts of data. So basically, at the very low level, what we do in the eBPF program is we say which process we're looking at. We say the kind of memory address of the original binary, kind of the offset. This is the thing that was executing, and it belongs to this memory section, basically. And that's all we kind of send off to and a list, of course, because we need the full stack, right?
Yeah.
And that's really all that we send off to user space. The kind of user space side of the agent still does some processing for that. It kind of aligns the memory addresses so that stuff like address space randomization, which is like a security feature in the Linux kernel, that doesn't have any effect on the addresses that we're seeing, so that if we're seeing this an address from one machine and an address from another machine, that they actually match, so that this continuous profiling thing across the entire infrastructure actually makes sense. And there's some like pretty low level engineering that people need to be aware of. I actually have a couple of kind of visualizations, if you think it's useful, that I could pull up, where I can show kind of exactly on the very low level operating system stack what's happening. Do you think that'd be useful?
Sure. Yeah, sure.
Let's see.
Perfect.
All right, cool. I think people can see this, but I can also share the slides that I've got here afterwards. So basically, what I wanted to show here are a couple of scenarios of what can happen and what we need to do to figure out what is the current function call stack, right? Because ultimately, like we've been saying, that is the raw data of profiling. So here on the left-hand side, what we can see at the very bottom is our main function, right? It calls A1, A1 calls B1, B1 calls C1, C1 calls top, and top is just for an endless for loop. And so ultimately, the stack that we would end up seeing from this program is pretty boring. It's just main A1, B1, C1, top. And that's what we would see every single sample be, right?
Yeah.
But how do we figure out that is actually the case? Well, that is what, for example, frame pointers can help us with. And for those people who are maybe not familiar with it, I got some kind of demonstration for this here. So frame pointers are special registers in the CPU and on the stack that we reserve to tell us where is the next higher frame or the next lower frame, if we look at it that way, right? So the highlighted section that I have here right now is for the function C1, right? So in the function preamble, basically what it says is, okay, push the RBP register, move the RSP, which is the stack pointer. So the where I am currently at executing, push that onto the move that into the RBP register, and then ultimately when we're done, we pop it and then return, right? And why this is useful is what I can show here. So if we look at this kind of sideways, we've got our binary, right? So we've got the setup of the frame pointer. That's where the arrow's currently pointing at, right? That was what we just saw with the push and then the move, right? That's setting up the frame pointer. And then we call some other function, and that's this instruction, right? This is essentially at the assembly level, the thing that our computers actually execute, right? We like to think that it's some higher level language that we're writing, but ultimately this is still what our computers execute. And the call instruction essentially can allow us to go anywhere else in this binary and continue executing there. And so that's what would happen here. And then there's the function preamble. It can set up some stuff about the function parameters and stuff like that. And ultimately, the thing that we've just set up is that eventually, when this other thing that we've called, you're going to return at this next address here, what we've called the return address, right? And the reason why all of this is really important is because ultimately, like I said, we call this other function, it executes, and it returns. That is the regular sequence of how the program would execute. When we want to figure out what is the current function call stack, what we do is we figure out what is the return address that we would have to get to, and we essentially just subtract 1, because that is, let me go back here, that is exactly the next upper function, right? The thing before we were called, right? That's where we want to find out, and that is essentially the address that we would save and end up pushing to user space. And then user space can and either already figure out what function name does that actually correspond to, or in our case, we actually delay this process as long as possible, so that the agent kind of can be as dumb as possible, so that it doesn't have to do any of that processing. But this is pretty cool, right? Like at the actual stack level, this is how it works. We actually read the real registers and so on. Now, people who are pretty familiar with this matter might already know that frame pointers, and we saw this previously here. Let me go back. We see this in the command that I have at the very top here. You actually need to enable on most compilers that you're kind of forcing it to have frame pointers. If that was the only way that we could profile things, that would be kind of sad, right? Because we would be forcing people to have specific compiler flags on and stuff like that. That's not exactly the goal of what we want to achieve at Polar Signals. We want everyone on the planet to be able to profile their software without having to add a library or an SDK or do any other kinds of code changes. And so, long story short, there are solutions to this as well. Here's another illustration. We just on the previous slide, we showed how we can walk a single frame, but ultimately we just keep on doing this until we're at the very bottom of the stack, and then we found the main function essentially. Yeah. But yeah, what to do when this magic thing that we've just used to walk the stack isn't there, right? Well, there's a really cool thing, and here we saw, this is the difference. This is typically what it looks like when you execute when you compile your program. You do not see frame pointers.
Yeah.
And so the answer here is, and I kind of hinted at it earlier already. We essentially do exactly the same thing as exception handling, and so we quite literally make use of this section that is in all binaries called frame or exception handling frames section. And so ultimately what this section tells us is it's actually much more comprehensive than what we need. It can actually tell you exactly how to restore every register at every function call reference, right? However, what I just went through with frame pointers is the only things that we need to restore are RSP and RBP. And as long as we can kind of understand how to restore those registers at every step of the stack, we can still do unwinding. And ultimately, I'm not going to go through all the details of this, but basically these frame sections are tables that tell us, what are the different steps and the different calculations at certain points and offsets that we need to do in order to restore those registers. And then we can effectively do the same thing as what we do with frame pointers, just without frame pointers. So the trick here is use this thing that is much more generic about restoring any register to restore only the registers that we need. And this is really important because only this way can we get it to be really cheap and really fast to look up, right? We can kind of compress. We don't need to actually give the whole frame section to the eBPF program. We can kind of compile it to a much more, much faster accessible one and a much more compact one, because there are various limitations that eBPF gives us. And so this is ultimately the secret sauce of why this kind of stuff can actually work. So yeah, ultimately, then we end up doing the same thing. We just need to have this kind of lookup table on the side that tells us, okay, I need to now do this calculation, and I need to do need to read memory from this many offsets from the current register and so on. And we can actually do it as well. So yeah, some pretty cool engineering, I think. And it's one of those things where you kind of need to go back to the basics. How does this freaking computer that I'm sitting in front of actually work, right?
Yeah.
So yeah,
It's pretty cool. I have two questions, right? Like first, why are these compilers not enabling frame pointers by default? Like, what is the problem? And the other one is, what do you exactly mean by restore the register, and what is the cost of it?
Yeah, great questions. So why not frame pointers by default? Well, this is actually something that we're trying to reverse. So basically, for a long time there was some truth to this, especially if we look back at the 32-bit era of processors. We actually had fewer registers available, and so not using the RBP register to store the frame pointer, but to store, to use as a general purpose register when the compiler, compiles our high level language to actual assembly code. That's where a single register actually makes sense. Now with like 64 bits, and I believe there are 16 general purpose, don't quote me on that, general purpose registers. One doesn't make that huge of a difference. And then, compilers may not even be using all of them in the first place anyways, because you can only store a 64-bit word in it. And you might end up storing, a pointer into heap memory instead, stuff like that. So historically, it was for performance reasons, and that's why some people still hold on to it. And there's in very, 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 very extreme situations, maybe some truth to it, because if we go back and see, there are 3 instructions per function call that we add to set up and tear down the sorry, it's two instructions. We always need to do the sorry, it's 3 instructions. We need to set up and then pop the register, right? And so, like I said, there are very, very few, very, very extreme situations where this might make a difference. But I would personally argue in those situations, it probably makes sense to kind of drop down to assembly level anyways, and kind of hand tune it anyways. So that would be my personal take on this. But and then the other aspect could be it very, very slightly could increase the binary size, right? Because again, we have more instructions.
Yeah.
So that's essentially that hopefully answers the question of like frame pointers versus no frame pointers. I definitely argue everyone should default to having frame pointers on, and only in the very extreme cases maybe turn them off, but probably more along the lines of in those very edge cases, rather just handwrite the assembly anyways. Sorry, what was the other question again?
Yeah, you were talking about restoring the register. What exactly does it mean? And is there like cost involved there? So, I mean, you were mentioning that you only need to restore a register for, these two, RBP and the other one, and you don't need the other ones, right? So what is the cost of it, and what do we mean by restoring the register?
Yeah, great question. So let's see. So here, this could be our stack, right? So our stack is just a collection of things that are put on top of the stack, and when we're done with executing the function, we can kind of remove things from this stack, right? The problematic thing is it's not static what we put onto the stack, right? And so one function might put 2 or 3 things onto the stack that are 64-bit words. The next one might just have its own parameters that end up, being the function parameters in our function signature, stuff like that. And so restoring the RBP register, what I mean by that is figuring out where within this variable blob of data do I need to search to understand, this is this thing, this is the RBP register. And that allows us then to understand, okay, this is where the last function left off. And so then we can kind of do the same thing again. Okay, and then from this point, where is the RBP register? And then we do that search all over again, and then we can kind of reconstruct the function call stack.
Okay, that's interesting. So basically, that allows you to traverse the call stack and reach the end, or let's say the bottom of the stack.
Precisely.
Okay, that makes sense. You mentioned about after you collect this data, you return it to, let's say, the user space, so the application or the agent can probably make sense of it and add more details to it. And you also mentioned about you want to make the agent as dumb as possible, so you delay the process of doing that. How does delaying the process of sending these data make the agent a bit more dumb?
Yeah, so the answer to that is essentially, like I said, all we get from as the result of this function call resolving, or sorry, from this stack walking is what we call this. The result is just the offset into the binary. So I don't know about you, but I don't remember what the offsets into my binary are and what functions they are. I'll be very impressed if there's a person who does. But joke aside, right? Like, we need to resolve this to the actual human readable function name, right? And this is the thing that is done typically. There are some exceptions to this, but typically is done using a format called dwarf, which is basically the same information that you use when you launch a debugger, right? And you kind of step through your code or something. it also needs to figure out, what are the instructions that end up executed, what are the variable names, all of this good stuff, right? And essentially, we use that same kind of information. The troublesome thing about Dwarf is it's Turing complete. So you essentially need to implement a virtual machine to interpret Dwarf. And that can be extremely slow. It can mean that you need to load vast amounts of data into memory. And so there's also kind of an operational reason for this. It's just, we want to keep all of this complexity outside of the agent so that it can be very stable, use the least amount of resources that it has to, and so on.
Okay, that makes sense. Cool. You also mentioned so I want to also go to the user space and see how that attaching to the application code happens. But I realized that we have been using the term eBPF, right, which is the the extended Berkeley Packet Filter. Let's talk a bit more about that, just to not assume that our viewers know what it means and
Yeah.
what exactly does it enable. Like, help us imagine a world without eBPF first, and then move to eBPF and how things would be better.
Yeah. So probably the best tool that we had before eBPF were kernel modules. So essentially plugins that you could load into the Linux kernel to extend it, right? And I'm gonna ignore a whole lot of problematic things with kernel modules. Like, it's complicated to load them correctly. It's complicated to keep them up to date. It's complicated to keep them compatible. Let's just for a second assume that isn't even a problem. Kernel modules can do anything you want, and so worst case, they can make your kernel crash. They can read things that they shouldn't. They can they're just code that's higher than root, right? Like, root is limited in some ways. The kernel is certainly not. This kernel can do random things with your hardware. It can write things to the hardware. It's immense amount of power, and therefore it's not unheard of that kernel modules can do some pretty bad damage.
Something like
And so
CrowdStrike.
I that is what just came to my mind. But I have to say I don't remember the exact details anymore. But I do believe the CrowdStrike outage had something to do with the kernel module.
Okay.
But don't quote
Yeah.
me on that.
Yeah.
But yeah, that is basically the world before eBPF, and eBPF allows us to safely extend the kernel because it's essentially a virtual machine that runs within the kernel. And before you're even allowed to load the program into this virtual machine, it verifies a bunch of things about your program. The most important thing is it effectively solves, or for a subset of programs, solves the halting problem. For those who aren't maybe familiar with this from like computer science, the halting problem essentially says we cannot determine that a program is ever going to halt, because what happens when you put the same program into itself? It's kind of a paradox. And the way that the eBPF verifier solves this, it says you can't actually create arbitrary programs. There can't be arbitrary loops. There can't be completely arbitrary accesses. There can't be go-to statements, or certain kinds of go-to statements at least. And so ultimately, it can say, yes, after absolute worst case executing 100,000 instructions, this program is going to terminate. I hand waved over a bunch of things there, but that's essentially, also in terms of the numbers, that's essentially how eBPF works. And then both statically as well as at runtime, this virtual machine makes sure that you're only accessing what you're allowed to access. So for the purpose of our profiler, for example, what's really good is we are allowed to access the memory of the process that is currently on the CPU. And so this is really helpful because we can actually do all this analysis that we've just talked about in a safe way. However, we cannot just read random arbitrary memory from some other process that isn't on the CPU right now. And so that has other reasons, also because it means that we are actually within the virtual memory of that process, and so on. And so it actually is really important that when we see a memory address within the memory of our process, that is actually valid within the context of this process. But I think if this is a confusing statement, I think that's okay. All we need to know is we can see the same memory layout as our process does, and that's really important for all of this to actually work.
Yeah, I think it makes sense. What I gather from your answer is that like kernel modules had some problems, mainly around the security or the verification phase. When I read about eBPF a bit, it also mentioned that the overhead is less in terms of execution. What makes it less overhead?
So I think there fundamentally you could have achieved the same things with kernel modules, but it would certainly require way more discipline. And with eBPF, it's simply impossible. Just this example of kind of no endless loops, it actually goes further. For a long time, you had to actually unroll all loops. So what that means is, that there were compiler kind of annotations that actually did this for you automatically. But at the end of the day, basically, you weren't allowed to write a normal for loop. You actually had to write each individual iteration of this for loop out. Again, the compilers actually helped you, so you didn't literally have to do that. But essentially, that's how it is. And so this means that the compiler can actually have a single long set of instructions that it produces, and there's no variability, there are no branches, and all of this. And so ultimately what this all means is the compiler is able to produce code that is very friendly to modern hardware, and so of course that makes a lot of code run really, really fast then.
Okay, yeah, that's really powerful. Cool. Let's move to the user space, right? Like because that's probably the even interesting part when it comes to reading profiles, because okay, you have collected the low level details, but now you have to attach it to like the real names of your function and stuff like that. What are other details that are attached, and how does that attaching works?
Yeah, so basically the very first thing that happens is we need to figure out, we look at, okay, which actual memory address is this from? And then we need to figure out across all of the processes that we have, which binary does this memory space actually belong to? So for which process was this basically loaded into memory for? We actually happen to know already the process. So all we need to do is look at, on Linux is /proc/ the process ID /maps. And those are all the pieces of binaries that have been loaded into memory for this particular process. So let me give you an example. If you use, I don't know, some library for some compression algorithm, let's say CSTD or something, right? Most of the time, in like C, C++, maybe even Python or Node.js world, you use a dynamically linked library. So you don't actually compile all of this into your process. There's some external library that you happen to call out into. And so when this happens, we still want to be able to profile it. And so therefore we look at, okay, what are all the pieces of binaries, all the object files, as they're called, have been loaded specifically for this process. And then we look at, okay, which one is the exact memory space? Aha, it's libzstd, for example. And so therefore we can then say, okay, this function was this address for this piece of binary. And then that is already enough information that we can send it off to the server, and the server can then associate, okay, there's this thing called a build ID, which all compilers add to a binary that they compile. And therefore we can say, okay, this memory address for this build ID, and these are the debug infos, what we talked about earlier in the dwarf format. Mm-hmm. These are the three things that I need to actually be able to now take this memory address and figure out using the dwarf data, it was actually this function name.
Okay, interesting. Yeah, I think this.
And of course, this we do for every single function in the stack.
Yeah. Okay. So yeah, I think that makes sense. So for the entire call stack, you have attached the function names and probably the address and so on. I think this looks good, and this makes sense when, let's say, in the happy path. What happens when the process dies? Are there some things that are changed and probably are not possible anymore? What happens then?
Yeah, I mean, there are some fundamental races that do exist here, because the good news is the unwinding process. Mm-hmm. That essentially, because we do it on a per CPU basis, there's no concurrency that can happen on that same CPU. So that's a very safe thing to happen. However, once we've successfully done the unwinding, we actually hand it off to user space, right? And from that point onwards, that's where, if the process dies within a few nanoseconds, that could mean that we can't actually figure out all of this information. But in practice, that almost never happens, or happens, relatively speaking, so slowly that it doesn't actually matter. And really the only thing, this is also really important, the only thing that needs to happen is for us to open a file handle against that object file, and we can still do everything. And so that is the first thing that immediately happens, right? Okay. And once we've obtained that file handle, everything's cool. We don't need to worry about needing to do anything very fast anymore.
Got it.
So it's a single, like, what is it, like file open or whatever system call.
Okay, that's interesting. So once you have the you are able to open the file handle, and then you anyways have all the information of what kind of binaries are loaded. You can look at the memory. Okay, that makes sense. This is cool. So from the low level, we've come to the let's say the user space where the agent is trying to do all of it. What if the agent dies? Like, what happens then? Are there some mechanisms to recover from that?
Yeah, I mean, at the end of the day, when the agent dies, and it just restarts, and it tries to continue where it left off. It does. So there are a couple of things where the agent tries to kind of cache the most expensive parts of what it does. So, for example, we saw earlier that we have to compile these like frame tables that are able to restore any register on the stack to one that can only restore the RBP register, right? Because that's only the only information that we need. That is a relatively expensive operation, and so therefore we try to cache as much as possible. Have we already done this process for this piece of binary, for example? Or there's more reason for this, which is most of the time you see the same processes on the same hosts many times, right? And so you want to just also avoid doing that kind of work multiple times. And then, when the agent crashes, it can actually kind of make use of that caching as well. And so it's basically a very small file cache that it can use for that. So that when it then starts up again, it can try to skip most of the expensive work that it needs to do.
Okay, interesting. In the examples that we talked about, we specifically focused on like the CPU usage, right? Let's take a couple of examples to understand like how it would change for understanding the memory usage or memory access or those kind of patterns, and or even network access.
Mm-hmm. So we actually never really talked about what is the trigger for this, right? Why does our eBPF program even run? And so that is ultimately the answer to this. But for CPU profiling, we attach it to something called a perf event. The way that you can think about this is we say, hey, dear CPU, every X amount of CPU cycles, please call our eBPF program. And so therefore we can make sure that every 19 like 1/19 CPU cycles that the CPU actually goes through, our program actually gets called. So that is how the CPU profiling works. And for memory, it's really not all that different. Basically, we say, okay, any system call that is called that actually allocates memory, please perform the function call, like the stack unwinding at that point in time. And then we can calculate all of the memory allocations that happen. Or if we want to understand heap, for example, the way that heap profilers tend to work is that we figure out, okay, which stacks allocated memory that hasn't been freed. And so you both trace the points where memory gets allocated and freed. And so the difference between those is the memory that is still actively being used. I will say this is actually something that's kind of area of exploration in eBPF, because with perf events, the kind of overhead is well understood and well controlled. With this kind of memory profiling, it's a little bit different, because you need to trace every single execution in order to determine, is this an execution that I want to sample? Whereas with perf events, we kind of at registering of the perf event say, I actually only want 19 samples per second, right? And so this is why like memory profiling is not a very widely done thing with eBPF today. But I do think this is going to change in the coming years as we kind of figure out how could we do similar things to kind of perf events for arbitrary hooks.
Interesting. So if we really go like really low level, it's actually periodic profiling and not really continuous, because you're doing like 19 technically, right? But yeah, at least comparing to on demand, it's like continuous and you don't have to worry about it.
Well, I will say that is how all profilers work. So that comparison is actually the same for ad hoc and continuous profilers. So the continuous part is actually just, you don't just look at it for a 10-second period. It's that you look at it for all of time.
Yeah. And I mean, 19, like 1/19 per second or 19 hertz per second. I think that's probably really fast to call it continuous anyway. So I think that makes sense. I might have asked you this question last episode as well, because I remember that like the number 19, and what happens when I increase this frequency or reduce this frequency? I guess if you reduce the frequency, it just goes to the end, like the right side of the spectrum, where I get less profile data. And if I increase the frequency, I get more profile data. Like, what is the advantage and disadvantage of both?
Yeah, I mean, ultimately, it all boils down to statistics. If you increase it, you gather statistical significance faster and over a shorter period of time. Whereas if you decrease the sampling rate, you increase that time that it takes to build statistical significance. And so that can be a dial depending on the environment. So typically we recommend 19 hertz everywhere, but we have some customers, for example, who dial it up in, let's say, a canary deployment, where they're routing 5% of all of their production traffic to this subset of nodes where they're trying out a new version that they want to roll out to the rest of their infrastructure. But there's a much smaller piece amount of infrastructure, and so for them to be able to say, yes, this is good versus no, this is not good compared to the rest of their production infrastructure, they want to dial that kind of ratio of data up, right? In order to have confidence in the data that there is actually not going to be a performance regression, or vice versa. If they're trying to improve performance, yes, we can definitively say this is actually going to have an improvement across the entire infrastructure.
That's pretty cool. So it gives you like a quick feedback if you have like more samples, because that reduces the time when you have like significant
correct
statistical like how do you say numbers that with confidence you can say, okay, this is better, this is not. Okay, that makes a lot of sense. How does it all change, like specifically talking about the agent side? How does it all change depending on different types of like environments, like I don't know, running on JVM or Node.js or Python or stuff like that?
Great question. If we have enough time, I can dive into a Python example. But so far, everything we've talked about is basically completely ignoring that any of these types of languages exist, right? But of course, that is not the reality. And the like very short answer is we need to build bespoke integrations for those types of languages. So interpreters, just-in-time compilers. Actually, just-in-time compilers are kind of somewhere in between, right? Because they end up being native code. They just don't emit an EH frames section somewhere, right? So we basically need to figure out what does, let's take JVM as an example. Where does the JVM store this type of information? Because the JVM needs to do like exception handling as well, right? So it becomes an exercise of where does the particular runtime, the particular language store all the necessary information. And again, like I do have some kind of graphics for this type of thing as well. If we have time, we can dive into it. But long story short is we figure out, what do the interesting structures that we need to read look like for different versions of, let's say, Python. And it tells us, okay, at this offset of this struct is where the function frame is, and then 18 bytes further is where the function name is, and 26 bytes, I'm making numbers up right now, but further is where the next frame, the one below is. So essentially, we build bespoke unwinders specifically for those languages then.
Got it. Okay. So I think the unwinding changes depending on how the data is stored and where the data is stored. But apart from that, the process stays same, right? Like once you know how to unwind this kind of environment, okay, it's going to be same. I mean, we have
at the end of the day, you always want to figure out what is the next upper frame, right?
Right.
And you just need to figure out how does this runtime know that itself, and we just read the same information and we perform the same thing.
Yeah, that's cool. We have a few minutes if you want to share the example or the graphics for Python.
Let me pull that up. So another pretty cool thing, maybe this was already obvious from the conversation, but this means that we can not only, profile native code, calling other native code. It can even mean that, the Python virtual machine or the Python interpreter that is written in C itself ends up executing Python code, obviously, but that Python code might end up executing native extensions, which in the case of Python is actually incredibly popular, right? Python is often kind of viewed as this language that is just there to kind of plug various things together, right? And we're seeing this a lot with kind of AI companies. Python typically is kind of the orchestrating language that then calls out to, I don't know, PyTorch or libcuda or stuff like that, right? Which does the really heavy lifting and all the number crunching. And then Python can kind of funnel that back into some other libraries.
Yeah.
And so we of course want to be able to kind of unwind the full stack. And so that's ultimately what happens here. We kind of, let's take the PyTorch example. The very top of the stack would be PyTorch code that gets unwinded. Then we figure out, this is actually Python. So we kind of sidestep and figure out what does the Python interpreter currently think is the function call stack. We do that unwinding. We jump back again and perform the native unwinding when we actually hit the Python interpreter itself. That is the result. But kind of how does that happen? And so here I'm skipping through a few pieces of information, but basically for each thread, Python has this PyInterpreter state, and it tells us, where can we find this information? Where can we find kind of the state? And the state tells us where is the current frame. So like we would say the top of the stack for native code. And then we can figure out, okay, in this case, we have one pointer for previous, one pointer for next, one pointer for interp, and then we have current frame. So what does that mean on a 64-bit system? That means at offset, let me get this right, 24, we have the current frame, right? That's basically how this works. We kind of reverse engineer how do these runtimes lay out the information that's important to them in memory, and we replicate it. And then, we can figure out what is the current frame, and then we're looking at the current frame, and that tells us all this really interesting information. It tells us about the previous frame. So now we already have the information to figure out what is the next lower function. And then here, actually, there are a bunch of interesting information that we end up communicating to user space as well, which is stuff like, we actually have the pointer that tells us about the function name, right? We don't want to store that and use in eBPF space, but we want to communicate enough information to user space so that user space can actually do this lookup itself as well. And yeah, how do we actually get to the point where we find this was it the PyInterpreter, I think, symbol? Well, all of the information is in these binaries. So here we're looking at, what are the dynamically linked libraries by Python? And we can see here the most important one to understand, this is actually a Python process, is the second one that we see here in this list, libpython 3.11. I happen to have a 3.11 example here. We look at the actual piece of binary, right? And we look for this specific symbol called PyRuntime. And then we can figure out, okay, this symbol is at the offset 557D20, right? And so this is actually information that is always going to be in this binary because it is required for the execution of a dynamically linked library. And so, long story short, what that means is we can safely assume that this is always going to be there. Okay. So that's pretty cool. And so ultimately that we can then use to kind of walk back. Okay, where exactly for this process here, this is what I talked about earlier, proc, and the process ID /maps. Now we can figure out, where is this dynamically linked library actually mapped into memory? And the important one here is the one that's marked R-XP. That is an actually executable section. And so now we know, okay, this is the range of memory that Python, that for this process, this is Python. And so therefore, that's where we would attempt to walk the stack as if it was a Python stack. That's ultimately all the steps that go into this. It's a little bit more complicated, and there are some hard-coded things actually as well, because some of this I kind of just glanced over and said these symbols are always available. That's not actually truly always the case. There are various compiler optimizations or compiler configurations that might not do it. And so, as long as we can figure out which version of Python is this, we can say, okay, we know what the memory layout of this looks like. And so therefore, we don't actually have to extract it. But kind of various mechanisms are in place so that hopefully we always are able to successfully perform the unwinding.
Okay, quite interesting.
Yeah, and this is the Python example, but fundamentally it works exactly the same thing, the same way for all the other kind of dynamic languages, whether it's Node.js, whether it's Java, whether it's, what else do we have? PHP, all sorts of languages.
Pretty interesting. Cool. I have one last question. Are there any use cases for profiling where eBPF isn't really required, or doesn't add a lot of value, for example?
Yeah, I think the best example here is what we talked about earlier with memory profiling. Today, this is best done by the allocator itself. Let me give you one example that's really popular in the ecosystem. There's a really popular allocator called JEmalloc. In especially the Rust ecosystem, for example, it's an allocator that Facebook created originally. And that actually has a profiler built in that does exactly the thing that I talked about earlier. It looks at every single allocation call and figures out, is this an interesting one that I want to sample right now? And if it is, well, then it saves it and potentially figures out if this piece of memory ever gets freed as well. And so this type of thing is best done in user space today and by the application itself. But hopefully this can change in the future. But today, that's the case.
Okay. Pretty interesting. I mean, there is a lot of things that we have covered today. So, and a lot of low-level details as well. So I think it adds a lot of value to people who are interested in learning how eBPF works or how profiling works in general. So thanks a lot for joining me today and sharing all the amazing details, really low level as well. I might have to go through the episode again just to understand a bit more on how things are working, do some searching and stuff like that. But I have a good high level understanding about the low level things, which is pretty interesting. Are there any resources that you would recommend specifically learning about eBPF and other profiling stuff that you mentioned, like people who are just interested into learning these things, how it works, or even probably trying to build something?
Yeah, so there's one more general thing that I would say about eBPF and profiling, which is eBPF can be used to do a whole lot of things, and profiling is actually one of the less common things. And so much of what we talked about today is way more specific to profiling than it is to eBPF. Really, all that there was to eBPF that we talked about today was, about the virtual machine and the verifier and the kind of restrictions that you have when you work within eBPF. But everything else, other than like which hooks do we attach this program to, everything else was just about profiling. And so if people are interested in eBPF, I first of all highly recommend that, because it's an incredibly powerful tool, specifically because really when you boil it down to it, it's you can execute arbitrary code at arbitrary triggers within the kernel. And so you can obtain just about any information you could possibly dream of at very low overhead. And so we're still seeing more and more eBPF tooling being built. And I'm very confident in saying that we're going to continue to see way more, because there's so much useful information in the kernel, and there's so kind of little that has been explored with this so far, I believe. We ourselves find ourselves building new eBPF-based tooling here and there. We recently built one to kind of do really specific network analysis that was really important to us. We actually happen to open source this as well. But my point being is, you can put this together in like a day and a half, and have extremely sophisticated diagnostics that were previously next to impossible to build. And if you did, then maybe it was extremely high overhead, extremely high cost for whatever reason,
or insecure.
Some resources that I love to use, in my opinion, there's nothing better than the Cilium eBPF library for Go. That's my kind of go-to, especially if I just kind of want to try something out really quickly. The tooling is amazing. The documentation is amazing. It also has really, really good documentation on the specific different types of hooks. So things that you can attach your eBPF program to. So that tends to be my first resource. But then there are definitely a ton of really cool and high quality resources on the BCC project as well as kind of libbpf is, other than the Cilium library, the canonical library for the entire ecosystem. So the libbpf organization on GitHub is super useful as well, and they have a ton of really useful resources.
Okay, pretty cool. Thanks a lot, and I'm really excited to release this episode soon, so our viewers can also learn about eBPF and profiling in general. And yeah, until next time we find some other topic, have a good one.
Sounds good.